that right now. It is. All right. So here's the situation we find ourselves in. We have a dead battery for the radio that we need to try and fix up. Okay? So this is actually a more complex question than it first appears. Okay? Because we can't just go down to the Radio Shack and buy fresh batteries. We're going to have to do some creative stuff. And we really need to have a good understanding of why does a chemical reaction happen? Why does a reaction stop happening? Okay? We really need to think about what we call reaction spontaneity. When is a reaction spontaneous versus non-spontaneous? And what is a spontaneous reaction? Turns out that this sort of real complicated idea boils down to a really simple, basic understanding. If a reaction happens, it is spontaneous. Okay? That is a spontaneous reaction. It happens. If a reaction does not happen, it is not spontaneous. The details, however, become important when we start to think about changing the conditions. For instance, when I pour some water out of my cup, okay, it does not, I can pour a little on the desk here and it doesn't freeze, right? This water is at room temperature. It's at 25 degrees Celsius. Delicious. But what if I had some water under different conditions? What would happen to the water if I poured it out? Okay. Plain water. What is the water doing? The water is freezing. All the water is doing is freezing. How come this reaction is spontaneous, whereas my reaction is not? What do you think about the temperature of this water? Yeah, it's cold. Below 0 degrees Celsius.
The temperature in the bottle is above 0, but the temperature in this cup is below.
I suspect that the water itself, watch this, it froze up into the bottle. This was a bottle of what we would call super cooled water. You've seen this super cooling effect before, right? Remember when we were freezing the stuff and it went down below its freezing point and then the crystals started to grow? That's what was happening with the water here.
How can you keep it stabilized?
So, a lot of questions here. Stirring it typically provides agitation that starts the crystals to grow. By not stirring it and keeping it in a very clean container with no cracks where crystals can more easily form, you can supercool the water. In fact, I've done this. If you go up in the mountains during the winter sometime, like on a really cold night up in the mountains, you take a bottle of water and you put it outside so that it'll sit and cool down very slowly. It will supercool. And then you can do something like squeeze the bottle and ice crystals will start to grow throughout the bottle. You might be able to do it in your freezer. It depends on how cold your freezer gets.
Would that have to be around exactly 0?
Nope. The water itself would start probably a bit below 0 degrees. Now, as soon as the ice crystals start to form, they're going to release heat. And that's going to warm the water up, which is why after that bottle froze, there was still water coming out because a bunch of the ice that started to form actually warmed up water next to it above 0 degrees, which stayed as a liquid.
What would happen to you if you stuck your finger into a bottle of super cool water?
You would warm it up. It probably wouldn't hurt you because you're not super cooled. So it's not like you would freeze. It's not like, yeah, you wouldn't freeze. Forming bonds releases energy. Exactly right. So this reaction of water freezing can be spontaneous or not spontaneous depending on the conditions, depending on the temperature, right? So what we want to understand is we need to understand why do chemical reactions happen? And to do that, we need to think about what we call the first law of thermodynamics. I should know that. But it basically, the second law of thermodynamics? I should look that up. says that the entropy of the universe must increase for a reaction to take place. For a process or a change to happen, the entropy of the universe, the change in entropy of the universe, second law, thank you. The entropy of the universe must increase. So, all right, the first step, we had to break this down. The universe we understand. That's everything. Everything that there is. Entropy is the key term here. Change we understand, increase we understand. What is entropy? So, the simple explanation, simple and highly misleading idea, is that entropy is a measure of disorder or randomness. Okay? And that is actually the idea we're pretty much going to stick with at this level, because trying to dive in to understand what we call microstates, or the way that the system can be arranged, is difficult. The basic idea here is that we can actually calculate the entropy of an object, of a system. Not the change, but the actual value can be calculated if you can understand and calculate how can it be arranged. What are all the possible ways that the system can be arranged? Do I have a very ordered crystal lattice where the atoms have to be in a very regular pattern? A very regular pattern has very little disorder or randomness. The molecules, the atoms, are very orderly in there. That would have very little entropy. A liquid, where the atoms or molecules are free to move around and can take on lots of different arrangements, has more entropy because the particles can be arranged in many, many different ways. Finally, a gas, where they take up a bigger volume and the particles are really far apart and can be arranged in even more ways, would have even more entropy. Okay? The amount of entropy from the start to the end is the change in entropy. The key thing to understand here is that we're talking right now about the universe, which is comprised of the system that we're interested in and the surroundings. So, the system doesn't have to become more entropic. The entropy of our system does not have to increase. The entropy can decrease, and in fact, in a lot of cases it does. For you as a human being to exist, you need to very tightly control the arrangement of the atoms and molecules in your body. You can't have them going around willy-nilly, or else you'll be a pile of goo. Okay? So, to decrease the entropy of the system, you expend a lot of energy. Most of that energy gets burned out and released as heat into the surroundings, making the surroundings have higher entropy. In fact, you release more heat so that the entropy of the surroundings goes up more than you're decreasing the entropy of the system. In every case for a spontaneous reaction, the entropy of this universe has to increase. That doesn't mean that the entropy of the system or the entropy of the surroundings has to increase. It means that the sum of the two of these values has to be positive. The change in entropy of the universe will increase. Now, this change in entropy is kind of difficult to calculate for the surroundings, since they include everything else in the universe. What we typically look at is we want to talk about the energy released by the system. And so we want to replace this term with thinking about how did the entropy change of the surroundings, how is that driven by the enthalpy change of the system? We want to look at the energy released by the system, because that energy goes into the surroundings, making it more disordered in a way that we can calculate and predict. So we want to really focus on the system, the entropy change of the system and the enthalpy change of the system. And to do that, we're going to create a whole new thermodynamic quantity called the Gibbs energy. And Gibbs energy is going to tell us whether a reaction happens or not, whether a reaction is spontaneous or not. In the simplest version of what we need to know, is the delta G value for a reaction positive, negative, or equal to 0. That's fundamentally what we need to know. What does the Gibbs value actually mean? It tells us the amount of work that can be extracted from a process, from a chemical reaction? How much work can it do? How much useful work can it do? That is the energy that won't be released as heat into the surroundings. How much energy can we extract from it to do stuff, do things that we want to do? Which is a really amorphous concept until you get into physics where you can rigorously define energy change and work in terms of particles moving and gases expanding and things like that that we don't really need to worry about at this level. So it's all going to be in joules. The units are all going to be joules per mole, kilojoules per mole, something like that. Entropy will actually be kilojoules per mole Kelvin, so that the kelvins cancel out. Questions?
I don't really know how to phrase this, but how does the entropy relate to heat change?
So they're related because if I heat up a system, the particles start moving faster. Particles that are moving faster have more randomness because they move around from one place to another more quickly.
But why do you have to, since you're trying to factor out temperature altogether when you're trying to find delta G, why do you multiply it by delta?
Well, temperature, it's not necessarily that I'm trying to factor temperature out. It's that I want to take temperature into account.
Yeah.
I know that changing the temperature changes the spontaneity of a reaction. So my equation has to take that into account in some way. And so it turns out that, the impact that delta H of the system has is going to be highly dependent on the temperature. If I release 1 joule of energy and I'm at 10 kelvins, that's going to heat the system up percentage-wise a big deal. Because the energy change will change the heat, right? Now, if I release 1 joule of energy and I'm at 1,000 Kelvin, that's an order of magnitude or 2 orders of magnitude less important change.
But why do you multiply the temperature by
what I'm basically doing is I'm taking this and I'm substituting it in here. And then I'm distributing the T through and creating this new function. Okay. Questions?
So that delta S after the T and the Gibbs thing is the universe?
This is the system. Instead of using delta S for the universe, we're replacing it essentially with this delta G function. And it's a little more complex than that. There's some other things that go into here. I don't think it's important for you to really get the derivation. This equation is on the useful equation sheet. Both of them are.
But that delta S refers to the system.
This is the system, and this delta H is the system. Okay, guys? So, we care about what the system does. That's much easier for us to measure because the system is a small part of the universe that we've defined. So we relate everything to the system. So now, again, let's go back to what the core important thing is here. What is the sign for delta G? Is it positive, negative, or 0? So, here's the thing. Delta G can be positive, negative, or 0. But if it's positive, it's a non-spontaneous reaction. If it's negative, then we'll have a spontaneous reaction. Now, our delta H and delta S values can be positive or negative, depending on whether the reaction is endothermic, exothermic, whether it becomes more random or less random. So there are several cases that we need to consider. If delta H is a negative value, that's exothermic, gives off energy, that tends to drive spontaneity, tends to make the reaction happen. If the entropy increases, a negative of a positive value will make it negative. The delta G will always be negative. Exothermic systems that have positive entropy change are always spontaneous. Now, being spontaneous does not tell us anything about how fast the reaction takes place. Diamonds converting into graphite, both of which are pure carbon, they're just different allotropes of carbon. Diamond converting into graphite is spontaneous under conditions of room temperature and atmospheric pressure. Your diamonds are slowly converting into graphite, very, very slowly. It will take millions of years for a diamond to convert into a piece of graphite. But you can see, if you go back in the geologic record and dig up cryolite mines and things like that, places where you have a little tiny diamond surrounded by a bunch of graphite. And it used to be a big diamond that slowly over millions of years converted into graphite. Okay, that happens. So the spontaneity depends on this. So, a negative delta G means the reaction is spontaneous. A positive delta G means the reaction, the forward reaction, is not spontaneous. It doesn't happen under the conditions we're talking about. Okay?
What conditions are we talking about?
So it depends on the specific reaction. But remember, for our diamond, we were saying at room temperature and atmospheric pressure, diamonds convert to graphite. Well, how did the diamonds get formed in the first place? That's one of those reactions where it changes depending on the temperature. Remember the water? Room temperature water, no freeze, doesn't convert, right? But if I cool this down below 0, the water will spontaneously freeze into ice.
Isn't there a point, though, that temperature doesn't matter, like at a critical point, temperature doesn't matter anymore?
No, that means where that's the distinction between liquid and gas is a little more complex than what we're talking about here.
Okay.
Keep it simple.
Okay, so it looks like the delta G is driven by the delta H.
Well, here's the thing. In this case, because this is a negative sign, it always changes this. But what if I have both of them have the same sign?
Then it could be,
Oh, it could be any value. It can be positive, negative, or 0. In this case, the reaction is endothermic. Okay, it takes energy to do. And, but the entropy change is positive. So a negative, this gives me a negative value for T delta S because of the negative sign here, and a positive value for delta H. Well, which one is bigger? Because that's what's going to determine what happens. Which one of these values is a larger value? And you know what? That changes because we can change the temperature. At low temperatures, this increase in entropy becomes less important. This T delta S becomes small at low temperatures. So this reaction would be non-spontaneous at low temperatures. That's like our graphite turning into diamond. Graphite turning into diamond is low temperature, not spontaneous. But if I increase the temperature to say 10,000 degrees or 5,000 degrees and a lot of pressure, then the T delta S term becomes much larger, a much bigger value. And the graphite to diamond, which was non-spontaneous at low temperatures, becomes spontaneous. Questions?
every reaction is standard, like a different standard temperature and pressure.
Well, we define standard temperatures and pressures as room temperature, 1 atmosphere of pressure, and things like that. But each reaction or each process will have, depending on what signs these guys have, will be spontaneous or not spontaneous, or will change depending on the conditions. But there are some reactions that will always be spontaneous regardless of the temperature, and will always be non-spontaneous regardless of the temperature.
There's no.
How do we know the delta H before the reaction actually happens?
So, we will get there. We'll get there in a minute. Okay, we're going to talk about how do we calculate these values in just a sec. Right now, let's just focus on the sort of, what does it mean?
So if, I don't know if you've gone there yet, but if the change in G equals 0.
So that's the key question, and this is really important. Here's the thing. Remember when I said we sort of needed to link this back to equilibrium? Delta G is 0, means that the forward and the reverse reactions are both equally spontaneous. So there's another way to think about this. Okay? So hold on just a sec. Negative delta G means that the forward reaction would be spontaneous. And the reverse reaction would be non-spontaneous. But I can reverse that and say, well, if it's positive delta G, that means for a reversible reaction, the reverse reaction could be spontaneous. And if I'm exactly at 0, that means that the system is at equilibrium, and both the forward and the reverse reactions are equally likely to happen. you can talk about, for an equilibrium system, these delta G values as not necessarily describing does it happen or not, but which direction is favored. Which direction is the system going to shift? Will I shift in the forward direction, or will I shift in the reverse direction, or am I at equilibrium? I typically like to approach equilibrium from a kinetics point of view based on the rates, but you can calculate two completely different sets of math. All the kinetic stuff, you can do a bunch of this entropy stuff and delta G stuff, and you get the same equilibrium answers.
So positive delta G is forward reaction is spontaneous, negative delta G?
No, reverse that. A negative delta G means the reaction as written is spontaneous. Negative delta G, spontaneous. Positive delta G, the reaction is not spontaneous, or you can think of it as the reverse reaction is spontaneous. And when delta G is 0, you're at equilibrium. Both reactions are spontaneous. Again, if the signs for delta H and delta S are the same, then you're at a system where it depends on the temperature. You can't say what is delta G, you say it depends. Am I at high temperatures when T delta S is important, or am I at a low temperature where T delta S is not important? And high and low are completely relative based on what are the actual values of delta H and delta S.
Wait, high temperature T delta S is important.
Yeah, because a larger T value, the bigger this value will be. Yeah, if I...
But the delta G, it says we need to determine if the delta entropy of the universe is positive. So
Right, and there's a sign change in here. There's a sign change in between universe and delta G.
right,
We almost always focus on delta G instead of the entropy of the universe.
wait. So is delta G the same as negative entropy of the universe?
The same as in the value? No. The same as in telling us predicting whether the reaction is spontaneous or not? Yes.
Okay. So if there's a positive delta G, it shifts to the left, and if there's
Yes.
a negative delta G, it shifts to the right.
Correct. Yes. All right, so instead of having you do this because of time issues, I'm going to run through it. But this is a question that's asking us, at what temperature would the boiling of bromine be spontaneous? In other words, where do we flip from being spontaneous or not spontaneous to spontaneous? Where does that equilibrium lie? Because equilibrium is the point where the forward and the reverse reactions reverse or would change from being spontaneous to non-spontaneous. The key, as I just talked about, right, is that what do we know about delta G at that flip point, at that equilibrium point? What did we just say?
0.
Delta G is equal to 0. In other words, our delta H minus T delta S is equal to 0. So we can rearrange this equation. Let's move the T delta S to the other side and bring the delta S back. We can arrange this equation to solve for the temperature. The key to getting a problem like this, particularly you see them around boiling or freezing, or they'll say at what temperature does the reaction become spontaneous? What temperature does the reaction become non-spontaneous? That point is the equilibrium point. That's the point at which delta G is 0. Okay? Question?
So the boiling point would be 0?
Remember, this isn't the temperature. This is the delta G. We're solving for the temperature by taking these values and subbing them into here.
That's the equilibrium.
It tells us we're at equilibrium. The boiling point would be the temperature at which causes us to be at equilibrium. Boiling is the equilibrium between liquid and gas.
Yeah.
That's the temperature. It's when we're at equilibrium between liquid and gas.
And what about when it's freezing?
Freezing would be liquid and solid.
But can there be an equilibrium between liquid and solid?
Yes, there can. The particles can be melting out of the solid into the liquid at the same rate they are freezing from the liquid into the solid.
So would it be solid or liquid?
It would be a mixture of both. It would be like a glass of ice water in a 0 degree room where it's just at 0 degrees, no energy going in or out. The water and the ice will both sit there.
Why is delta G 0 for the
We are at equilibrium. The boiling point, the freezing point, those are equilibrium points where the reaction can shift forward or backwards depending on if we put energy in or take energy out. But we are at equilibrium. And that's the key distinction for our delta G equals 0.
When there's an equilibrium between solid and liquid water, does it look like it's changing?
No, you don't see any apparent change.
Even though the parts that were liquid are becoming solid?
Well, what happens is usually on the interface of the ice crystal, maybe over a long period of time, you might see some sort of general change. The mass of the solid, the mass of the liquid will remain constant.
Yeah.
They're both spontaneous. So this is the point at which we would just flip. So you would say, okay, let's go through and solve this. Remember, this is kilojoules, and this was joules. So we go through and solve this, and we'd say, oh, at temperatures above 330 Kelvin, the boiling would be spontaneous.
Wait, why does it switch from being 31, the
Kilojoules versus joules.
Okay.
You got to make those balance. Questions, Kevin?
Okay, if you were to do that same equation to find the freezing temperature for
Uh-huh.
liquid to solid,
Sure.
would the delta S be different and
Yep.
delta H be the same?
Nope, they'd both be different. It would be a different equation, different entropy and enthalpy changes.
Wait, how would the enthalpy be different?
Because if we'd be going from a liquid to a solid instead of from a liquid to a gas, it takes different amounts of energy to change those bonds. All right? So, to do this, in order to really figure out what's going on here, in order to calculate to whether a reaction is spontaneous or not, we need to know how to calculate delta S and delta G values. We have to be able to go through and actually figure those out. Okay? Fortunately, there is nothing new in what I'm about to show you. It is all stuff you have done before if you remember back to chapter 6 when we dealt with delta H. The processes, the ways we calculated delta H are exactly the same things we do for delta S and delta G. Do you remember these sheets? I gave you a new copy because I figured some of you lost them. So, one way to do it, one way to do this, we can do the actual calculations. We do like products minus reactants. We do some equations, Hess's law. There's some different things we can do. But, okay guys, but before we get into working with all the math, we need to have a sort of a better understanding of just going to predict for delta S. It's relatively easy for us to sort of look and say, hey, that reaction looks like it will release energy. I burn something, it releases energy. We need to have a little bit of an intuitive sense of, hey, does this reaction become more or less random? Does it become more ordered or less ordered? I need to be able to just predict, not calculate, but predict the sign for delta S. Positive or negative. Does it get bigger or smaller? That's what I care about. And to do that, we need to think about some of the things we already talked about. If I have a solid, does that have more or less entropy than a liquid? It has less. Solids have less entropy. The atoms are all rigidly arranged, fixed in place. Liquids, they're free to move around. Where would a gas fit into this mixture? More entropy. Gases have more entropy than liquids. Liquids have more entropy than solids. So if you look at a phase change, or some chemical reaction where you're making a lot of gases from solids, the entropy would be increasing. And your delta S would be positive because you're changing solids into gases. Gases have more entropy than solids. Also, if I take two pure substances and I mix them together, if I have something dissolving, that has a higher entropy. There are more ways that the particles can be arranged if there's two different types of particles that can be around each other. Mixing increases the amount of entropy. Okay? What? No, that's my S. My delta S is for a change from solid to liquid. You're looking up the S for the liquid or the solid. That doesn't give you the delta. So, a couple more things, guys. You gotta write these down. You gotta know them. Okay. So mixing increases entropy. Kevin. So, other things that will have more entropy. If you have more particles, your system has more entropy than if you have fewer particles. More particles, more ways that they can be arranged around each other. Okay, so more particles, more entropy than fewer particles. Also, on a molecule for molecule basis, a large molecule has more entropy than one small molecule, 1 to 1. Typically what happens is one large molecule breaks apart into a bunch of little pieces. That's an increase in entropy. A bunch of little pieces have more entropy than one large molecule. But one large molecule has more entropy than one small molecule. A large molecule has lots of different ways it can bend or wiggle, okay, which gives it more entropy. And there's a whole branch of study around what are called degrees of freedom and all this kind of stuff you can learn about if you go and take, third year chemistry. Chemistry. No, well, these kind of rules don't really help us with enthalpy as much. Enthalpy is more intuitive, like you burn something, it releases energy, that kind of system. Generally, the examples are fairly clear. So, that's it. That's basically solid, liquid, gas, mixtures, more particles, particle size. Those are the things you want to think about when you're trying to predict, hey, does this change have an increase or decrease in entropy?
I'm just kind of confused about the whole delta S thing, because if you want to define S for like a solid, then wouldn't you have to do like each microstate?
Yep, but that's all done for us in these charts. So when we get to the math, we're going to do like a products minus reactants, taking into account the coefficients. And you can do that sort of products minus reactants math. And we'll come back to this. You'll be able to see it. Hold on just a sec. Just sit. So products minus reactants, you remember this? We've done it a bunch of times before. We looked the values up. We can calculate the delta S. What we're actually looking up is S values, not delta S. These are absolute entropies for the substance. We can also do it for delta G. Okay, and I will give you that slide again tomorrow. We can calculate delta G using the equation. We can also use the charts and do products minus reactants or Hess's law. Hess's law is where you have the multiple equations and you got to flip them around or multiply them. All right, tomorrow we'll spend some more